Alright, welcome back. This is lecture 47 in this course. The topic of today's lecture is information theoretic measures of predictive accuracy. In the last lecture, we left at this question that what measure should we use to basically calculate the predictive accuracy of a model. So, how do we calculate how accurately does the model predict future data? Okay, so we need to basically quantify. Let's say you take any model M1. What is a model? It composes of your likelihood assumption and prior assumption. So let's say these are your model assumptions. Okay, so let's say this is your model. So how good is this model at predicting some future data? Let us call it unseen data, at predicting some unseen data. Okay, let us call the unseen data just y. Okay, so how good is the model, or let's say just y future. Okay, so how good is the model at predicting this future data? So we need to come up with some measure that can give us how do we quantify whether the model is able to predict this future data or not. Okay, so how do we do this? So actually, one line of methodology in evaluating the predictive accuracy or model performance is that we have these information theoretic measures of predictive accuracy. Okay, so it starts with a simple assumption that predictive accuracy is actually reduction in uncertainty. So predictive accuracy is actually reduction in uncertainty. Okay, what does this mean? This means that how much uncertainty is reduced by learning an outcome. Okay, how much uncertainty is reduced by learning an outcome. Okay, what this would imply is that let's say model makes some prediction about reaction times in an experiment. Let's say these are the predicted reaction times by the model, and then you observe the actual reaction times are, let's say, here. Okay, somewhere here in the middle. Then what would happen is that model will learn from this data. Okay, and now the future predictions will be even more certain. Now model makes more certain prediction that actual reaction times in these kind of experiments would be close to this, right? So in this case, the model's certainty about predicting future data is increasing because the data that you observed was basically very compatible with the model's predictions, right? However, if model makes these predictions and let's say the actual data that you observe in an experiment is somewhere here, okay, which is not captured by these model predictions, then what would happen is that model will need to take into account this new information, and the new predictions of the model might look something like this. So now the uncertainty has not reduced, it has in fact increased. Okay, so that's the perspective we are starting with, that predictive accuracy of a model is given by how much uncertainty is reduced by seeing that data. Okay, so if this is the model, then how much uncertainty is reduced by observing this outcome y future, by observing this data. Okay, but how do we calculate this? Okay, so there are terms here. So there is a term called reduction and there is a term called uncertainty. So how do we measure uncertainty and how do we measure reduction? Okay, how do we measure uncertainty contained in a distribution? Okay, so that brings us to this question: how do we measure uncertainty, okay, contained in a distribution? Okay, in the context of model evaluation, we will need to calculate uncertainty in the posterior predictions of the model. Okay, in the prediction, what predictions model make, right? So we need to capture uncertainty in posterior predictions of the model. Okay. So we ask, how do we measure uncertainty for a distribution? So we want that such measure of uncertainty should have certain properties. For example, it should be a continuous function. Also, as the number of outcomes, number of possible outcomes increase, uncertainty should increase. So we want this measure to capture certain properties, right? So for example, let's say a model predicts, let's say, only this much space, okay, has, let's say, so this distribution has less uncertainty compared to, let's say, this distribution, which predicts a huge number of possible values, right? So as the number of possible outcomes increases, uncertainty should increase. So it should be a continuous function, it should have these additive properties, right? So we want this uncertainty to follow certain properties, right? And it should also capture property like this versus, let's say, this. So which one is more uncertain? What do you think intuitively? Let's say this is distribution 1, this is distribution 2. So although number of possible outcomes are same in this and this, basically they are in the same range, but the distribution 2 is very, let's say, certain values have very high probability densities, but certain values have lower probability densities. So this distribution is more certain about what kind of outcomes you would observe. This distribution 1 is less certain about what kind of outcomes you will observe, because it is all values are equally likely within this range. Okay. So in 1 and 2, intuitively 1 is more uncertain, okay, than 2, which is less uncertain. Okay. So we need a measure of uncertainty which captures some of these intuitions, that if in terms of probability distribution, if probabilities are skewed for certain values of the outcome variable, then that has less uncertainty compared to a model which, let's say, gives almost equally likely values for a range of values, right? So we want to capture all these intuitions. So there is a brilliant measure which has all these properties, and which is one of the sort of breakthrough measure in this direction. It's a basis of information theory as well. That measure is information entropy. Okay, so measure is given by Shannon, so it's information entropy. So it's a core of information theory. So information entropy will give you how much uncertainty is contained in a distribution for any probability distribution. Okay, and the formula is this. Let's say you have a probability distribution P such that, let us consider a discrete random variable which can take values, let's say, let's consider a discrete random variable which can take values x1, x2, x3, x4 and xn. Okay, and it has its probability assigner function f of x, which will assign these probabilities. So this is the probability mass function of this random variable associated with a random variable, and assigning, let's say, these probabilities p1, p2, p3, p4 and pn. So these are probabilities for each possible value of this random variable for each outcome. Okay, so how do we measure information entropy of this? So idea is this, that information entropy of this probability distribution P is given by negative of expected, okay, negative of expected log of probability. So something like this, pi into log pi. Okay, so this is the formula of information entropy. So this is the measure that we are going to use to calculate uncertainty. Let us take an example to understand it. So let's say, let us consider a binomial distribution where your random variable can take, let's say you toss a coin 3 times. Okay, you're tossing a coin 3 times. Okay, what are all the possible outcomes? 0, so let's say we're counting number of heads, 0, 1, 2, 3. Okay, and let's say you choose a binomial distribution as your probability distribution. So what probability values it is going to assign if it is a 3 coin toss experiment? So the binomial distribution is given by 3 factorial divided by x factorial. So and 3 minus x factorial and theta to the power x, 1 minus theta to the power n minus x. So let's say theta is 1 by 2. Okay, so for when x is equals to 0, okay, then this would turn out to be 1, this would become 1, this would become 1 minus theta to the power 3, and if theta is 1 by 2, this is 1 by 2 to the power 3. So this would be 1 by 8. Okay, similarly this would be for 1, this would be 3 divided by so 3 into theta into 1 minus theta square, right? So which would be 3 into 1 by 2 into 1 by 4. So this would be 3 by 8, and this one would be theta square into 1 minus theta into 3. So this would be 1 by 4, 1 by 2, 1 by 8. So again 3 by 8, and this final one would be 1 by 8. Okay. So these are probabilities assigned by a binomial distribution, okay, to each outcome of this random variable. Okay. Now how do we calculate information entropy here? So information entropy will be given by negative of summation of, so basically summation of pi log pi. So basically 1 by 8 into log 1 by 8 plus 3 by 8 log 3 by 8 plus 3 by 8 log 3 by 8 plus 1 by 8 log 1 by 8. Okay, so that would give us, because these terms are repeated, so basically minus of 2 by 8 log 1 by 8 plus 6 by 8 log 3 by 8. So you can solve this further and figure out what is information entropy. Okay, so that's how we compute information entropy or uncertainty contained in a distribution. Now you think about this particular problem, that let's say, let's take even a simpler example. Let's say a random variable x can take only 2 values, 0 and 1. Okay, let's say in this case the probability assigner function you are using, it's such that, I mean it could be basically, let's say theta is equals to 0.5. So both these will get probability 0.5, 0.5. So this is p1, this is p2. Okay, both are 0.5, 0.5. Versus you use theta equals to 0.9. Now the probabilities assigned would be, let's say 0.9 and 0.1. So this is p1, this is p2. Okay, now in which case you think there is more uncertainty? Basically when you toss a coin, let's say this is a coin toss experiment, let's say this is heads and this is tails, right? This is heads, this is tails, right? In which case there is more uncertainty? Well, in this case you are almost sure that 90% of the times you are going to get a tails. In this case you are less sure, because 50% of the times you would get heads and 50% time you get tails, right? So intuitively this is this contains more uncertainty and this contains less uncertainty, and this is what will turn up when you calculate information entropy for this distribution versus this distribution. So, information entropy would be larger for this one and would be lower for this one, larger for this and lower for this. So, it captures that intuition. Also, let us say if you have a third outcome, head, tails and don't know, versus you have only two outcomes with let us say same probability, almost same probabilities, then this one would have with three outcomes would have more uncertainty because there is an extra outcome. So, it is also has additive properties. So, you can try a few examples and see how information entropy matches with your intuition. Okay. So, that is the idea of information entropy. So, we will use information entropy to capture or to measure uncertainty contained in a distribution. And why is that important for us? Because we want to measure reduction in uncertainty. Okay, so now we have a measure of uncertainty, but how do we measure? Do we measure reduction in uncertainty? Okay. So, how much uncertainty is reduced by learning an outcome? So, this is actually given by a measure called KL divergence. Okay. KL divergence. I am not going to go into too deep into all these measures because we are not going to use precisely these matrices, but they are important for understanding where we are going. So, the metric we can use to measure reduction in uncertainty is KL divergence. What KL divergence tells you is that uncertainty induced by that how much uncertainty is induced when you try to predict a distribution P using probabilities from distribution Q. So, basically if you use this distribution Q to predict P, then how much uncertainty is induced. That means how much uncertainty increases. So, this is not directly giving you a measure of reduction in uncertainty, but this is giving you totally opposite thing, the measure of increase in uncertainty. So, if we just do negative of KL divergence, that would be a measure of reduction in uncertainty. So, that this tells you that how much uncertainty is induced when we try to predict this distribution P using probabilities from distribution Q. So, basically you have two distributions now, P and Q. So, when we try to predict this distribution P using probabilities from this distribution Q, then how much uncertainty increases or how much uncertainty is induced. Okay. So, this formula is given by, this is actually a measure of cross entropy. Okay. So, in a way entropy difference. So, the formula is given by this summation of Pi log Pi minus Qi log Qi. Okay. So, basically we are using information entropy formulas here. So, basically difference of information entropies, but this term, the distribution that we are trying to predict is used in both these terms, right. So, first one is let us say I 1 to n Pi log Pi minus summation I 1 to n Pi log Qi. Okay. So, this will give us KL divergence. Okay. But what is P and Q here? Okay. So, let us say Q is posterior predictive distribution or posterior predictive density function. Okay. So, Q is basically distribution of your posterior predictions, and what is P? So, let us say P is the true distribution that underlies your data. Okay. So, Q is the distribution of your posterior predictions, the distribution that you want to use to predict P, and P is the true distribution of your underlying, a true distribution that is actually behind your data, and this is exactly your goal. You want a measure of that how good is your model at predicting the true distribution of the data, right. So if your model is really good at predicting true distribution of the data, then this distance between P and Q would be small, right? So the scale divergence actually gives you how far is this true distribution P from your model Q. Okay, so Q is distribution of posterior predictions of your model. P is the true distribution that underlies your data. Okay, so this is not data, but the true distribution that underlies your data. Okay, so we want to compute how far is Q from P. Okay, and that can be given by KL divergence. But there is a problem here. Okay, and what is the problem? That we really do not have access to P. We do not know what is the true distribution P. If we would know that what is the true distribution P, then there is no problem at all. Then we can directly use the scale divergence to get a measure of predictive accuracy. Okay, but we cannot do this because we do not know what is P. Okay. So what we do instead is that we take another model. So basically distribution of posterior predictions from another model, let's say R. So this is one model. So this, let's call it model Q. Let's say there is another model, model R. Okay, I'm writing the distribution of posterior predictions of this another model R. Okay, and let's say this term DKLPR gives us KL divergence from R to P. So basically, if we use probabilities from this distribution R to predict this true distribution P, how much uncertainty is induced, right? So this distance is between the model Q and the true distribution P, and this is the distance between model R and the true distribution P. Okay. So although because we do not know what is exactly this true distribution P, we cannot compute what are these absolute distances between P and Q and between P and R. But what we can do, we can compare these two distances to check which model is closer to the true generative process. So although we cannot compute these absolute distances, we can compute the difference of these distances, basically difference of KL divergence from Q to P and KL divergence from R to P. Okay, basically we can compute this metric, KL divergence from Q to P minus KL divergence from R to P. Okay, so we can compute this. Okay, so this is a measure of relative distance of model Q from a true distribution relative to another model R. Okay. Now, how this would help? So let us apply the formula. So KL divergence of P is given by summation P log P minus summation P log Qi. Okay, so this is KL divergence from Q to P, and this one is summation Pi log Pi minus summation Pi log Ri. So I have applied formula of KL divergence for this and this, right? Now what we have here is that these terms are same, right? Summation Pi log Pi, summation Pi log Pi. So they will cancel out. So the remaining term that we get is summation Pi log Ri. Okay, or you just take negation, summation Pi log Qi minus summation Pi log Ri. This is what we get. So this is the relative distance of model Q from the truth relative to model R. Okay, so we just need to compute this term, right? If you want to write it in a different way, then you can write it like this, log Ri minus Pi log Qi. So this will give us relative distance of Q from the truth with respect to R. Okay? How close is Q to the truth compared to R, right? Now, if let's say, so here we are assuming that these probabilities are discrete, but that is not necessary. That well, these probabilities could very well be, so these distributions could very well be continuous, and in practice you would have mostly these distributions would be continuous. So rather than using summation, then in that case you will need to use integration. Okay, so the actual metric that you will be using would look something like this: P of, so true distribution of your future data. Let us write future data as y nu. Okay, true distribution of your future data. So this is this term actually. Okay, into log of, so this is coming from some model. Okay, so let us call it log of r. For now, let us just write log of r given some parameter theta, which is conditional on some old data, let's say observed. We are trying to capture the predictive density, right? So predictive data, the posterior predictions, right? And here it is p y nu and q phi given y obs, right? And of course, this thing is integrated with respect to dy nu, and here as well dy nu. Okay, so you can do an integration rather than this summation. So actually, if we think about this, these two terms are independent of each other, right? So you will compute them separately. They are not going to influence each other, they are independent. So you can compute them separately and then take their difference, right? So each term can be considered to be giving us basically how much is the evidence, okay, or how close is that model relatively to the truth, right? So for example, this whole term gives us how close is this model Q to the truth compared to R. Okay, so this term actually gives us some quantification of how close is this model Q to the truth, and this term gives us some quantification of how close is this model R to the truth, right? So in a way, the actual term that we are interested in is this, that true distribution of your new data and this log of, now this thing is actually distribution of your posterior predictive data. What is actually a posterior predictive data and what the distribution of posterior predictive data would look like? So posterior predictions are generated like this. So let's say this is some prediction ypred. It is generated from your likelihood function. Let's say your likelihood function is r. So it is generated from your likelihood function r theta hat, where theta hat is basically estimated based on your already observed data, basically your training data. Okay. So if we want to think about this distribution, what is actually the distribution of these predictions, these posterior predictions, then the distribution of the posterior prediction will be actually given by likelihood of these basically likelihood of observing these predicted data given theta hat, such that theta hat is trained on y obs. Okay, so basically this is the likelihood of observing any future data. Okay, so not predicted, we should write new data. Okay, so likelihood of observing this new data given some estimate of theta hat from its posterior distribution. Okay, so I can actually write it like this: likelihood of y nu. You can write it in typical way as we write likelihood of theta hat conditional on, okay, so likelihood that theta hat will generate this new data y nu such that theta hat comes from posterior distribution of theta given the training data y obs, okay, and negative of this. So, this gives us a measure of, and then its integration with respect to y nu. So, this gives us a measure of predictive accuracy of a particular model, let us say R. Let me replace this L by R just to indicate that this is a part, we are talking about a particular model R. Okay. Now, we will build on this. So far we have basically figured out what measure can be used to calculate relative predictive accuracy of a model. We will build on this and we will arrive at the point that what exactly we can use to calculate predictive accuracy of a model in the Bayesian framework. So, for example, how we can use this term to calculate predictive accuracy of a model. You might have gotten some idea, but there are still some unresolved questions. For example, how do we calculate this? We can calculate this. This is just the predictive density of the model. It is called predictive density. Basically, it's the likelihood of observing these new data points given some particular samples from the posterior distribution. But how do we calculate this, right? So, we will resolve these questions and we will arrive at a precise measure for calculating the predictive accuracy of a model. Okay. All right. So, we will meet in the next lecture for this. Thank you.